Hello everybody, welcome to your section 4 notes. You should have your green sheet out with you. So if you need to, pause the video, go find your green sheet. We should be turned to the part in your green sheet that says section 4, and it should say physical properties up at the top. Alrighty, so if you need to, pause the video, go find it. If for some reason you forgot your green sheet at school, right, we've warned you many times about this, but you can find a copy of the Section 4 green sheet on Canvas. You need to go to your Applied Chemistry homepage, click on Class Resources, and then underneath Green Sheets, you will want to click and download the Section 4 notes. All right, so at this point, you should be ready to go, so let's get started. We're going to be talking about physical properties. At this point, we've already started our investigate in class. We have made the clay dough sample, and next time I see you in class, we'll be doing some experiments on them, or next time you see Mr. Arrow or Miss Stout. All right, so let's get started with our notes. All right, so when we're talking about the word property, it's another word or a synonym for the word characteristic or a trait, right? Or just ways that we can describe how something acts when we do something to it. All right, so physical properties, and these are going to be the ones that we're going to cover in class. These are not the only physical properties that are out there, but these will be the ones that we focus on and that you're going to be tasked with understanding. So actually, before we write down these examples, let's take a second and to the right of where it says physical properties, let's write in this definition. So properties that can be observed without changing the chemical makeup of something. So I can observe or perform an experiment to collect data on this substance, and it will not change the identity of the substance, right? So I can look at water and tell that it's transparent without actually changing the chemical formula of water. All right, so here are examples. We can observe the state of matter or the color, the texture, uniformity, strength, elasticity, bounce, and malleability. I just want to make sure there wasn't any more there. All right, so if you need to pause the video, make sure you have all, what would it be, 7 of those written down. All right, welcome back. So we're going to first start out by talking about texture, and you should be familiar with this term. I'm sure you've heard or used it before. But a definition that we're going to use, it's the feel or the appearance of a surface of a substance. So we're specifically looking at the surface of the substance. All right, so this is one that we probably would not need to perform an experiment to observe. We just need to look at it. Uniformity. This is how consistent a material is throughout, right? Does it look the same the whole way through, or does it look like there's different parts? Or does everything in the material seem evenly distributed? So when we're looking at this picture, right, of this classroom, does it look uniform throughout? Right? I would have to say no, it does not. We see many different people of different races, different genders, wearing different outfits, right? It does look like they are using one uniform laptop. It looks like all of them have the Apple laptop, but even then it's not completely uniform because they have different colors and different types of laptops, right? And I'm sure you've noticed this little blue box in the center of the page. It says homogeneous equals blank uniformity. So if we're looking at something and it looks to be homogeneous, right? We have talked about homogeneous through section 3, then we're going to say that it is uniform. But we know that, right, if it was a homogeneous solution, it would be uniform. Now, some things that might appear homogeneous but are not, something like a colloid, right, is not actually uniform throughout. So we want to not only just use our observation, but also the knowledge that we have of, right, is this made of the entire substance the whole way through? Right? Is this a true solution as a mixture, or would this be a colloid type of mixture? And we'll talk about what type of mixture we created in lab later. All right, the next one we're going to talk about is strength. Right? And this is how well a material withstands the application of force. Right? This is a picture of me growing up. I was a really strong kid. I don't know what happened. But if you take a look at the picture at the top right of the screen, you can see there's a bunch of cars there on these steel racks. Right? So what we're looking at here is how strong that those steel racks need to be in order to hold the weight of all of those cars. Right? Because they need to not only withstand it at first for a second, but it needs to withstand it over a long period of time. All right, now we're going to talk about elasticity. All right, and the number one thing I want you to think about when we're talking about elasticity is a rubber band. All right, so this is how well a material will resist deformation and return to its normal size or shape after force has been applied to it. So if I have a rubber band and I stretch it, right, what would happen when I let go? Right, the rubber band is going to go back to its original shape, right, and that's what we call elasticity. So for something to be elastic, it not only needs to be able to stretch, but the important part is that it also returns back to its original shape. All right, so rubber band is a perfect example, but let's look at some other examples that we might have. All right, so here is a splat ball. You may have seen one of these growing up. If not, you might want to look into getting one of these. They're a lot of fun. They get quite dirty real fast, so they don't last too long. All right, so this is a perfect example of elasticity. It completely flattens out once it hits the surface after being thrown to the ground, but you can look in slow motion, it slowly goes back to its original form. All right, splat ball is perfect examples of elasticity. All right, but this is designed to be elastic. So let's take a look at something that, right, you might not think so much as being elastic, right? Sometimes when we look at or think about bouncy balls, right, they're so hard that we can't imagine that they actually compress and then return to a shape. But when we look at when a bouncy ball is bounced off a surface in slow motion, we can see that they really are elastic. Take a look at the shape of the bouncy ball when it hits the ground. You can see it squish, right? But then it goes back to its original shape. So the bouncy ball or the super ball here is definitely elastic, right? So those are some two pretty good examples. Now let's take a look at something a little bit closer to home, right? And this is usually a favorite video of students. So let's look at the human face, right? Are we elastic, right? If we come into contact with something, do we return back to our original form? Ooh, so at first, you can see that the soccer ball is the one that's compressing, right? And then we start to watch. Take a look at his nose, right? The tip of his nose is staying where it was. The top of his nose is moving. Imagine if we were not elastic, right? We would get in collision like that, and your face would permanently be stuck in that position, right? I don't think you're going to get a teeth at homecoming if you're all right. Let's take a look. We can see his face is back to normal. All right, so that is elasticity. Remember, not only the ability to stretch or deform, but also to come back to its original shape. I think I'm just scrolling through YouTube now. Here we go. All right, now we're going to pick up at bounce. This is one we should all be familiar with. This is the material's ability to return to its original position when it's dropped from a given height. So something with a greater ability to bounce, right, is more likely to return exactly back to where you dropped it from. So if I drop a bouncy ball from this height and it returns to this height, right, it had a great bounce. But something that is not so bouncy, like a bowling ball, if I drop it, might only bounce a couple inches off the ground. All right, so when we are dropping something, right, when we're holding that object, let's say we're holding a bouncy ball, right? When I'm holding it, it's pure potential energy, right? It's not moving. It's just held at a certain height with the potential, right, to move at greater speeds. Once I let go of it, right, the further it gets down, the faster it's going and increasing in its kinetic energy, right? And it will max out at its kinetic energy when it's closest to the ground. All right, next one, and this is probably a new term for you. I would definitely star this one because this is one that students often mix, and this is malleability. This is the bottom one on the first page of our section 4 notes, and this is a property of a material to be hammered into various shapes without breaking. Right, so if you've ever watched a TV show or a movie that's set back in a time where people were fighting with like swords and bow and arrows, you probably witnessed a scene with a blacksmith. And the blacksmith had like a hammer or a mallet, and they were hitting a piece of metal, right? And it was making that sound. I'm sure you can imagine the sound it's making right now, right? So what they're doing is they're beating that metal into a shape so that they can have something sharp like a sword or an axe, or something rounded like a shield, right? And the reason that they can do this is if they heat the metals up to a certain temperature, right, they become more malleable and they're able to beat them into the shape that they want, right? And we can even we can still beat a piece of metal over or we can beat a piece of metal without it being heated up very hot. It just won't change its shape as fast. All right, so you can read our little blue box here on the bottom left. An applied force distorts the shape, and the substance keeps that shape without breaking. So this is not exactly the opposite, but very different from elasticity. In elasticity, it returns to a shape, but in malleability, right, it keeps that shape. All right, let's turn to the next page in our green sheet. And we're going to be talking about composite materials. So when you get back to school on Monday and Tuesday, we're going to be starting the second portion of our Investigate Lab. And you're going to turn one of your clay dough balls into a composite material and keep one as it is from what you made in class. And we will test different things to see, right, if making a composite material change some of the physical properties of that substance. Right, so a composite material is when the properties of a mixture can be changed by adding different materials. So we're putting multiple materials together. And this creates a new heterogeneous mixture that makes use of both properties of each component. Right, so if you're looking at the pictures here, we have a piece of wood that has multiple pieces of wood layered there in different directions. Right, you might call it plywood. And we're taking advantage of those different pieces to increase the strength. Sorry about that. Hopefully you said bless you. I appreciate it if you did. Another example, right, and you can take a look here at the picture on the bottom right, and this is a skin on a jet. So skins on a jet are made of composite materials because we want it to be light, right, to not weigh down the airplane and make it harder or make us use more fuel to get it above the ground. But we also want it to be strong and durable. So that's why they have to use a mixture of two materials. All right, so some uses for composite materials would be bulletproof clothing, right, like a Kevlar vest, skin on jets like we just talked about, or armor on tanks. Helicopter blades are often composite materials. You might use like a field hockey stick or a lacrosse stick or an ice hockey stick or a baseball bat that's made of composite materials. And while composite materials do sometimes make things better, right, there is a downside to them. So it takes a lot of time and money to come up with new composite materials, right? We need to test them and make sure that they're safe and approved for the uses that we have. And they're using rare materials that are not commonly found. we have to mine for these materials, and the more we mine, the harder and more dangerous it is to mine more of them.